So thank you very much for the introduction, Christos. And it's really nice to be back at Northwestern. So the last time I was here was at the end of my postdoc at the end of 2017. So it's been quite a while. And I'm excited to be back because this is where my love for metal organic frameworks and structural characterization, and also, of course, the detoxification of chemical warfare agents, if everybody's familiar with the Farha group work, this is where it all started. So, and this is what I'm still doing in my own independent career at Concordia University, which is in Montreal, in case anybody hasn't heard of it. So today I'm going to tell you about some of the work that we're doing in my group, which is making rare earth metal organic frameworks, specifically with pyrene-based linkers. Of course, characterizing those materials as thoroughly as possible, and then using them for the detoxification of a mustard gas simulant. So today I'm hoping to show you is obviously the motivation behind our work and the detoxification of chemical warfare agents and their performance and all of that, but also how understanding the structure of these materials is really important for understanding performance, and then being able to use that as a feedback loop to keep designing better and better materials for this specific application. And so, doesn't want to click. There we go. So in my research group at Concordia, we're mostly focused on the design, synthesis, and characterization of a specific class of MOFs that are rare earth cluster-based metal organic frameworks. And so those are MOFs that contain the rare earth elements, scandium, yttrium, and the series of 15 lanthanoids on the periodic table, but where the metal nodes in these MOFs are specifically multinuclear metal clusters. And we're interested in these types of MOFs for a few different reasons. First, because they're relatively underexplored in the literature, so it gives us the opportunity to design and discover lots of new crystalline materials. Also, because of the high and variable coordination number of the rare earth elements, we can gain access to unique building blocks and intricate MOF topologies that are quite difficult to obtain, or in some cases not possible at all, to obtain when using other metals on the periodic table. We're also interested in the rare earths, and more specifically the lanthanoids, because of their optical and magnetic properties that we harness for some of the applications that we work on, although I'm not going to talk about those ones today. And so when it comes to making these rare earth cluster-based MOFs, these are just some examples of the rare earth clusters that we have access to and that we can use as building blocks to make these MOFs. And so you can see the diversity in these clusters in terms of the nuclearity, their connectivity, and their geometry. And this type of diversity is really, really exciting as a MOF chemist, but it also poses a very significant synthetic challenge because it can be quite difficult to control the generation of specific clusters in situ during the solvothermal synthesis of MOFs, particularly the high nuclearity hexa, hepta, and nonanuclear clusters shown here. And so if we look into the literature at MOFs that have been made with these high nuclearity clusters, we see that the synthesis always involves the use of a fluorinated modulator. So something like 2-fluorobenzoic acid or 2,6-difluorobenzoic acid. Originally in the literature, it was thought that we needed those fluoro groups to give some hydrophobicity to the system. So to protect these clusters while they're forming and to protect them from hydrolysis specifically in situ. But more recently, researchers have shown that the bridging ligands in these clusters, which are traditionally assigned as bridging hydroxoligands, mostly through crystallography, are actually bridging fluoroligands, or at least a mixture of bridging hydroxo and fluoroligands. So it turns out the requirement for these fluorinated modulators is because we need those fluoro groups to actually make these building blocks. Another challenge that arises when we try to make these rare earth cluster-based MOFs is that rare earth elements, when you combine them with carboxylate linkers under solvothermal conditions, they have a thermodynamic preference for forming these rare earth oxo chains. And so there are quite a few examples of these rare earth chain-based MOFs that have been reported in the literature, but comparatively fewer examples of rare earth cluster-based MOFs. And so I'm going to start today by telling you about some of our cluster-based MOFs and their photocatalytic properties. But I'm also going to show you some chain-based MOFs that we've discovered by accident or through serendipity throughout the process of making our rare earth cluster-based MOFs. And so this slide just kind of summarizes our contribution to this field over the last 4 years or so, where we've shown that you can make rare earth analogs of the well-known zirconium-based MOF called UiO66. So this MOF has these hexanuclear clusters that are 12 connected, bridged by the terephthalic acid linker and the overall FCU topology. So Mohammed Adaudi and his research group had previously shown that you can make these clusters in situ, and they had shown some other MOFs with FCU topology, but our report in 2021 was the first example using just the regular terephthalic acid linker that's used to make UIO66. We've also shown that you can make rare earth analogs of the well-known zirconium-based MOF called MOF 808. So we call this MOF rare earth CU45, so CU stands for Concordia University. This has these 6 connected hexanuclear cluster nodes bridged by the benzene tricarboxylate linker and the overall SPN topology. And then we've also shown that you can make this MOF here that we call rare earth CU10. It has these non-nuclear cluster nodes bridged by the pyrene linkers and the overall SHP topology. And I'll talk more about this specific MOF in a few minutes. And so in all cases, we are able to make these metal organic frameworks using yttrium and then the lanthanoids ranging from gadolinium to lutetium, so the late lanthanoids. And in all cases, we can confirm that our cluster nodes do have a mixture of bridging hydroxo and bridging fluoro ligands in them, although the exact ratio of ligands to each other depends on the exact metal organic framework and a little bit on the conditions that we use. And so I'm going to tell you a story today about our pyrene-based MOFs specifically. And this was one of the first projects ever in my research group at Concordia. So we started this in 2019. And it was taken on by my first PhD student, Victor Quesada Novoa. And so we were interested in making new rare earth MOFs with this pyrene-based linker. And I'll explain the significance of the pyrene in a few minutes. Now, I'll admit that when we first started this work, I was not entirely sure how to generate specific rare earth clusters in situ, or even what the resulting framework topology would be. I had spent my whole career at Northwestern working on zirconium-based MOFs, and zirconium is quite different from the rare earths. But what Victor and I did is we sat down and we hypothesized experimental conditions that we thought should be possible to generate a high nuclearity cluster in situ based on everything we'd read in the literature, and then hopefully a new MOF. Now that I've been working with these MOFs for the last 5 years or so, we have a much better idea of how to control specific clusters in situ, including their connectivity, and how to target very specific MOF topologies. But it's taken a long time for us to be able to gain that knowledge and to get there. And so to start this, Victor first synthesized this tetratopic pyrene-based linker. He then reacted it with a rare earth precursor using 2-fluorobenzoic acid as the modulator in DMF at 120 degrees Celsius. And he obtained these nice and beautiful single crystals that you can see here. And so we were able to determine the structure of this MOF using single crystal X-ray diffraction, actually with the help of Amy Sargent, who used to be a crystallographer at Northwestern, so people maybe know her. And so you can see these beautiful single crystals. And what was interesting is that the non-nuclear cluster node of this MOF is actually disordered over 2 positions. So at first we thought maybe it was a rare earth 18 cluster node, but actually it's the non-nuclear clustered over 2 different positions. And Victor was first able to make this with yttrium and terbium, and that node gives this double 6-membered ring building unit that's needed to make the SHP topology. And so in addition to those large and beautiful single crystals, Victor was also able to make this material in bulk, so nice microcrystalline powders. So you can see the powder X-ray diffraction patterns here show that the material is crystalline and phase pure. And this MOF also has permanent porosity, so we can activate it under vacuum at 120 degrees Celsius to get these nice type 1 nitrogen gas adsorption isotherms with surface areas of around 1,800 meters squared per gram, and showing that these triangular pores are about 10 angstroms in diameter. And so the reason that we're interested in making MOFs with these pyrene-based linkers is because we want to use the pyrene linkers as photosensitizers to generate singlet oxygen, and then to use that singlet oxygen to go on and selectively oxidize and detoxify mustard gas. Now, specifically, we don't use the sulfur mustard compound in our lab. We use this simulant here called 2-chloroethyl sulfide, which is safer to use, easier to handle, and has very similar reactivity to the real chemical warfare agent. And we're interested in doing this because when you have a metal organic framework, you have these photosensitizers arranged in a fairly rigid manner in three-dimensional space. And you can use these MOFs as heterogeneous photocatalysts, which means that you can pretty easily recover them and reuse them. And we can excite them using these homemade LED setups that we've made here with any wavelength, depending on where the photosensitizer absorbs. So in the case of pyrene, we actually use UV LEDs. And so just to take a step back then, so why are we interested in the detoxification of sulfur mustard, or where does the motivation come from? So sulfur mustard is this compound here. It was first developed in the 1800s and then used in a large-scale attack during World War I. So it was during this time that it became known as the king of the battle gases because it caused more fatalities than phosgene, chlorine, and cyanogen chloride combined. That's because this compound here, it's a powerful blistering agent. It causes severe burns to the skin, eyes, and respiratory tract. And it does that because it readily loses a chloride. It forms a cyclic sulfonium ion, which can alkylate DNA and cause programmed cell death. Now, unfortunately, sulfur mustard is not just a problem from World War I, but there are some reports, some even more recent than these ones here, of this compound being used against soldiers and civilians in areas of the world under conflict. Now, even though most nations have declared that they have gotten rid of their bulk stockpiles of sulfur mustard, which is great, unfortunately, this compound is very easy to synthesize, which means that it's always a potential threat in any area that's under conflict. And so the ways that people currently get rid of these bulk stockpiles of sulfur mustard is either by high temperature incineration, but this is not very environmentally friendly. It gives off sulfur dioxide, hydrochloric acid byproducts, or through dumping this compound into the ocean, where it slowly hydrolyzes over time. And so we were interested in seeing if we could find a more environmentally friendly, sustainable way to detoxify bulk stockpiles of sulfur mustard, ideally through oxidation or through the use of a heterogeneous photocatalyst like a MOF. And so if we look at the sulfur mustard compound, there are three main ways that you can detoxify or degrade it. There's a hydrolysis pathway, so this is what happens when the compound is dumped into the ocean. But unfortunately, an acidic byproduct is given off during that hydrolysis reaction. And also sulfur mustard is an oily compound, so it's not very soluble in water, meaning that it takes a very long time for the hydrolysis to occur. There's also a dehydrohalogenation pathway, but it requires the use of a base and it liberates an acid. And there are different side products and byproducts that can form here, which are quite toxic themselves. And so we choose to focus on the oxidation pathway because ideally we can just use molecular oxygen as an oxidant. But you also have to be careful with this pathway here as well because it has to be selective to generate the sulfoxide. Because if you over-oxidize this compound and you generate the sulfone, this is almost equally as toxic as sulfur mustard itself. So it's the selective oxidation of the sulfide that is key. And so there are different ways that you can selectively oxidize sulfides to sulfoxides. And one way to do that, that's been shown in the literature a lot in the past, is to use singlet oxygen. And there are also different ways that you can generate singlet oxygen, but one way to do that is to use a photosensitizer. So something like a porphyrin-based compound or a pyrene-based compound. And so just very briefly how this works, our photosensitizer absorbs light, you generate the singlet state of that photosensitizer. If you have efficient intersystem crossing, which can be aided by a heavy metal like the rare earth elements that we use, you can generate the triplet state of that photosensitizer. And if that triplet state has the right energy, it can transfer its energy to ground state triplet oxygen, generating singlet oxygen, which is a reactive oxygen species, and can do this selective oxidation. And so Victor takes his metal organic frameworks, in this case, rare earth Cu10, which has these pyrene-based photosensitizers. He suspends them off in a methanol solution, adds the mustard gas simulant, shown here, and then bubbles the reaction with oxygen for 20 minutes to make sure that it's an oxygen-saturated environment. And what we see here is the conversion versus time profile for both of these MOFs. So in both cases, the reaction goes to 100% completion. It is selective for the sulfoxide, so we don't see any presence of the sulfone. And when using only 0.5 mole% of each of these MOFs as catalysts and irradiating with UV light, we see half-lives for these detoxification reactions of 5 and 3.5 minutes for the yttrium and terbium analogs, respectively. And so these are actually some of the fastest half-lives that have been reported in the literature for this reaction to date. And so what we want to do is we want to understand why Cu10 is such a great catalyst for this reaction, but we also want to look into the literature more and learn more about all the different types of pyrene-based MOFs you can make, and what exactly are the structural features of those MOFs that lead to a great photocatalyst. And so we can compare our catalysts, yttrium and terbium Cu10, to some other pyrene-based MOFs that have been reported in the literature before. So this is NU1000 and NU400, of course, developed right here at Northwestern University. And I was part of this research. I started this research here at Northwestern as a postdoc. So even though my Cu catalysts are better, according to this slide, I want to say that it's better than my own work. so we can look at the pore aperture size as well as the density of pyrene chromophores, okay? So the pore aperture size is important for the diffusion of reactants and products, which is going to be important for a catalyst. But the density of pyrene chromophores should also be important for the generation of singlet oxygen, right? And so if we look at NU1000, it has these really large 30 angstrom pore apertures, so great for diffusion, which is why it's such an excellent catalyst for lots of other applications. But it has a very low density of pyrene chromophores. So it ultimately gives rise to this kind of moderate half-life that we see of 6.2 minutes. If we look at NU400, this has a very small pore aperture size, so not very good for the diffusion of reactants and products, but it has a high density of pyrene chromophores, ultimately giving rise to a pretty slow half-life. But if we look at Cu10, it has this kind of balance between pore aperture size and pyrene chromophore density, where we have this kind of moderate pore aperture size, so not too bad for diffusion, this moderate density of pyrene chromophores, and ultimately giving rise to these faster half-lives that we see. But is this really the whole picture? Is it just pore aperture size and photosensitizer density in the MOF, or is there something more to it? And of course, we can't really look into that further if we only have 4 MOFs to look at. And so the next thing we wanted to do was test how the identity of the rare earth element in the metal organic framework would affect the generation of singlet oxygen and the subsequent photocatalytic results. And so initially, Victor made yttrium and terbium Cu10, and then he worked quite hard after this to make the lanthanoid analogs ranging from gadolinium to lutetium. And so the reason we thought that the identity of the rare earth element could play a role in the generation of singlet oxygen is twofold. One, because we have the heavy atom effect required to make the triplet state of the photosensitizer and generate singlet oxygen. So maybe that could play a small role. But also because these rare earth elements, these lanthanoids, have emitting states, these 4F energy levels, that can accept energy from the pyrene-based linker. So there's the potential for linker to metal energy transfer to occur in some of these analogs, specifically the ones from holmium to ytterbium. And so we wanted to see if this linker to metal energy transfer that can theoretically occur would be a competitive pathway with the generation of singlet oxygen and thus affect the photocatalytic results. And so the first thing we had to do, of course, was make all these different analogs of rare earth Cu10. And so Victor was able to do that. And these are the powder X-ray diffraction patterns showing that all the MOFs are isostructural. We were also able to determine the structure of all of these materials through single crystal X-ray diffraction. So Victor was able to make those large, beautiful single crystals for every single analog of this MOF. And they're also permanently porous with surface areas ranging from about 1,500 to 1,900 meters squared per gram. We take a look at the ground state photophysics. We see that the absorption spectra shows primarily pi to pi star based absorption. So it's dominated by pyrene photophysics. And the emission spectra also is dominated by pyrene photophysics, where we see a mixture of monomer and exomer based emission. Now, to understand if that linker to metal energy transfer was actually taking place in these MOFs, the ones where it's theoretically possible to occur, we needed to collect some near-IR photoluminescence data. And so this data was collected by Francisco Yurura Villanueva, who was a PhD student in Mark Wilson's group at the University of Toronto at the time, and he's now a postdoc. So in order to probe whether this linker to metal energy transfer was actually taking place, we needed to see if we could observe the near-IR emission coming from these lanthanoid elements. And so we do, in fact, see that from holmium, erbium, and ytterbium Cu10, confirming that this energy transfer here is taking place. And that can be a competitive pathway with the generation of singlet oxygen. We did not see any emission for the thulium analog, but this is to be expected since thulium is well known to undergo cross-relaxation processes. And in the crystal structure, we can see that those thulium ions are only 3.9 angstroms apart, which is well within the distance for cross-relaxation and quenching to occur. And so now we can take a look at the photooxidation kinetics. So we can see here the conversion versus time profile for all these analogs of Cu10. And we can see the half-lives for these reactions. And what we see is that for some of these MOFs, particularly the ones where that linker to metal energy transfer is taking place, we do see slightly slower reaction kinetics, so slightly longer half-lives, confirming that although it doesn't make a huge difference, the identity of the rare earth element is important when considering designing these photocatalysts for this application. Okay, so this is where a little bit more about structure and crystallography comes into play. So throughout Victor's time making all these different rare earth Cu10 analogs, which as I mentioned before, he was able to make with yttrium, but also gadolinium to lutetium, he accidentally discovered some other new MOFs here called rare earth CuO6 and rare earth CuO5 that have these rare earth chain-based nodes. So even though these were not the MOFs that we were specifically targeting, we're always looking for rare earth cluster-based MOFs in my group, we were still very excited to have these new materials, these new frameworks, and to kind of expand our library of pyrene-based MOFs to understand what exactly it is about the structure of these materials that lead to a champion photocatalyst. And so Victor was able to make rare earth CuO6 with only the early lanthanoids, so lanthanum to europium, and rare earth CuO5 with only the late lanthanoids, gadolinium to lutetium. But no matter how hard Victor tried, he was unable to make large single crystals of these MOFs that were suitable for single crystal X-ray diffraction. So I'm showing the structures here now because we know what they are. But at the time, we had no idea the structure of these MOFs. All we had were some powder X-ray diffraction patterns. And so to kind of probe further and to actually understand the structure of these materials so that we could understand their properties and their photocatalytic activity, we needed to dive a bit further. So first we have the powder X-ray diffraction patterns for this MOF that we were calling CuO5. And we started by just trying to compare them to some powder patterns for other MOFs in the literature that had pyrene-based linkers. And so we found this JXNU5 as well as ROD7. And you can see that the powder patterns have kind of a reasonable match, but not really overall that convincing. This particular MOF also does not have a lot of Bragg reflections, which made it particularly difficult to try to determine a structure from the powder X-ray diffraction patterns. So Victor traveled to Germany, where he did a 4-month exchange and worked very closely with Dr. Max Turbin and Professor Robert Dinnebeer's group at the Max Planck Institute for Solid State Research. And he then traveled to the ESRF to collect high-resolution powder X-ray diffraction data, as well as total scattering data, to try to gain a better understanding of what this material actually was. And so from that high-res powder X-ray diffraction data, we still were not able to do a proper Rietveld refinement due to the severe lack of Bragg reflections in this powder pattern. Victor was able to do a poly refinement where he found that the unit cell parameters for CuO5 did match pretty well with those of JXNU5. But of course, just a poly refinement still doesn't really tell us that much about the overall structure. So from there, we turn to this total scattering data and specifically to the pair distribution function analysis. And so, as I mentioned, Victor collected this data at the ESRF. And so we compared the pair distribution function, so specifically from 1 to 10 angstroms. So the experimental data for this MOF that we were calling dysprosium CuO5 to models that Victor made, taking the JXNU5 MOF that had been previously reported and just inserting dysprosium into the material, and taking this ROD7 MOF, which had been previously reported, but switching the metal for dysprosium. And so what we can see from this pair distribution function data is that the local structure of CuO5 matches quite well with that obtained from the model for dysprosium JXNU5. And so if we combine that with the fact that the polyrefinement also matches quite well for this MOF, we're now reasonably sure that the material that we have is isostructural to this MOF here. So we didn't just look at the dysprosium analog, but we also looked at the pair distribution function data for all of these different analogs of CuO5. And what you can see is that in all cases, the pair distribution function matches quite well with the simulated models for JXNU5 with these different rare earth elements. So this MOF is also permanently porous. So we have these nice nitrogen gas adsorption isotherms, BET areas up to 660 meters squared per gram. And we can see in the scanning electron microscopy images these types of kind of spherical structures that we obtain, which if we look a little bit closer, seem to be made up of little cubic and rectangular crystallites. So these were unfortunately not suitable for single crystal X-ray diffraction or for electron diffraction, which is why we turned to the total scattering data. So the next structure we wanted to understand more about was this MOF that we were calling rare earth CuO6. So here we have the powder X-ray diffraction patterns for this material. So we can see that all the MOFs we were making were isostructural, but at the time we didn't know what the structure was. And again, no matter how hard Victor tried, he couldn't make crystals that were large enough for single crystal X-ray diffraction. So we were fortunate enough to be able to send one of these samples, the lanthanum CuO6 sample, to Rigaku, where Pierre measured some or collected some electron diffraction data for us. And he was able to solve the structure of this MOF, which is now shown here. And so pretty amazing that off of these really skinny plate-like crystals, we could get a full structure solution. This still kind of blows my mind, honestly, but I guess for people that are doing micro-ED a lot, this is pretty normal now. But I think it's pretty amazing. And Pierre was able to solve this full structure by merging 5 different data sets. And we were able to plug this into Topos Pro to determine that the topology is FRL. Again, this is a MOF that is permanently porous with surface areas ranging from 600 to 770 meters squared per gram. And then you can see those crystals under this scanning electron microscope. So they do not look like crystals that to me you would be able to get a structure from. So it's very exciting for us. Okay, so now we can actually look at the photooxidation behavior. So now that we know the structure of these 3 MOFs, we can look at how they perform for the photocatalytic detoxification of the sulfur mustard simulant, and then try to understand how structure relates to function in these catalysts. And so these are just the kinetics, the conversion versus time for the 3 different series of MOFs. And here at the bottom, I've summarized the fastest MOF catalyst from each of the 3 series. And so initially I told you that our hypothesis was that it was a balance between pore aperture size and pyrene density that was most important. But if that were the case, then we would expect that lanthanum CuO6 and scandium CuO5 should have faster half-lives than terbium Cu10, because the pore apertures are still quite large, only 1 angstrom smaller, but the density of pyrene chromophores is much higher. So we would expect that we should be able to generate more singlet oxygen from these MOFs. But in fact, these half-lives are, although comparable, they are a bit slower. And so taking a closer look at the structures then, we thought maybe it's not just the balance between pore aperture size and pyrene density, but it must also have to do with the arrangement of pyrene photosensitizers and specifically their spacing distance. And so if we look at terbium Cu10, for example, we have pyrene in this structure that is angled at about 60 degrees from each other with a separation of 11 angstroms. And so we think that this separation in this structure should be enough to hinder, or at least partially hinder, excimer formation in these MOFs, which can be a competitive pathway for the generation of singlet oxygen. Whereas in lanthanum CuO6 and CuO5, even though we have these really high density of pyrene chromophores, they're stacked in relation to each other and very close. So in CuO6, they're parallel to each other with a separation of only 6 angstroms. And in CuO5, they're alternating layers at 90 degrees to each other, but with a separation of only 4 angstroms. So we think that in these structures, we can generate more excimer formation, meaning that that excimer formation is competing with the generation of singlet oxygen and making these catalysts not quite as fast as Cu10. So this is all something we wouldn't be able to understand without knowing the absolute structures of all these materials in great detail. And so with that, I hope to have shown you some examples of these rare earth MOFs, both comprised of cluster and chain-based nodes, that they all have fairly fast half-lives for the detoxification of a mustard gas simulant, and that by understanding the structure, we can start to understand structure property relationships, particularly the correlation between the way that the pyrene chromophores are arranged in the structure and the generation of singlet oxygen. And we hope to continue to contribute to the fundamental understanding of just how to design these MOFs and characterize them, as well as their applications. So with that, I would like to thank my research group shown here. So this is us in Montreal in the summer. I'm kidding. Montreal actually has very nice, beautiful summers. These are all the funding agencies and all of the collaborators for their help. Particularly, we work with a lot of crystallographers. So I'm not a crystallographer myself, so I wouldn't be able to do any of this without the help of Dr. Hatem Titi from McGill, Dr. Amy Sargent, Maxwell Turbin, and Prof. Dinnebeyer from the Max Planck Institute, of course, Pierre Lemegers, and our other collaborators as well. And so thank you for your attention. Questions? Mm-hmm. The cutoff? Yeah. So we think it's related to the preferred coordination number. So if you look at I'll try to where's the best example? I guess I can start on this slide. So if you look at rare earth CuO6, which we can only form with lanthanum to europium, if you actually take a closer look into that rare earth chain-based node, all of the lanthanides have a coordination number of 9 or 10 in that node. And it's required to actually form that specific type of node. Whereas if you look at rare earth CuO5, we have a mixture. Some of the lanthanides have a coordination number of 9, but most of them have a coordination number of 8. And so I think because it's difficult to force the early lanthanoids to have a coordination number of 8, we can't make these specific motifs that are unique in this structure, or at least it's more difficult. And we have the same problem with our cluster-based MOFs. So far, we've only really been able to make them with the late lanthanoids. All the rare earths in those have a coordination number of 8, sometimes with very low occupancy of like a terminal water in a 9th position. But we're having a lot of difficulty trying to make the early lanthanoids, probably because it's difficult to force them into that specific coordination number in geometry.